The title of the paper is Vector Control of Dual Three-Phase Induction Machine Based Flywheel Energy Storage System using Fuzzy Logic Controller. This was the work done by my student Muhammad Dawood as his master's thesis. The presentation contains flywheel energy storage system basics, then importance of multi-phase machines, then proposed dual three-phase induction machine based flywheel energy storage system, modeling of the machine. It's called dual three-phase induction motor or asymmetrical six-phase induction machine. Then fuzzy logic-based vector control algorithm for induction machine. Simulation results are presented, and then the conclusion. So in renewable energy sources or islanded microgrid and transportation application, flywheel energy storage is an important element that plays a significant role due to its potential benefits such as high energy density, long life, fast dynamics, high charging rate, as well as discharging rate and charging and discharging range. Reliability of flywheel energy storage system is an essential characteristic when it is applied to support critical load or fault ride-through purposes. So this work proposes the exploitation of multi-phase machines reliability feature in the flywheel energy storage system applications. The vector control of asymmetrical six-phase machine is presented. Current control, which is required for the vector control implementation, is performed using fuzzy logic control algorithm. In the conventional method, hysteresis current control is generally employed, but that is replaced by fuzzy logic current control in this paper. The fuzzy logic control ensures fast and smart vector control that suits the nature of the critical applications. The validation of the proposed dual three-phase induction machine or asymmetrical six-phase machine based flywheel energy storage system is done in MATLAB Simulink, and a case study is presented under normal condition and faulted condition. Now this is the basic block diagram of a flywheel energy storage system where we have the magnetic bearing followed by a motor generator unit, then the shaft, then composite flywheel, vacuum chamber, and here is we have the vacuum pump, then we have a power conditioning unit, then it is connected to the transmission line. So flywheel energy storage system works by accelerating a rotor to a very high speed and then maintaining the energy in the system as a rotational energy. So this is an energy storage system. Unlike battery where the density is low, here the energy density is very high. So flywheel energy storage is a combination of electrical machines, flywheel, which is a mechanical device, then power electronics circuit, and the bearings. Emerged as a dynamic energy storage system. In flywheel energy storage, induction motor is driving the flywheel, which works as a motor while storing energy and as a generator during releasing energy. So this unit, which is motor generator unit, it is working as a motor when it is storing the energy, and it is working as a generator when it is discharging the energy. So in this paper, what we are going to do is to replace this motor by multi-phase machine, and vector control scheme is implemented for this machine using fuzzy logic current control algorithms. Now, why multi-phase machines are used? Because of the inherent advantages that they offer. So we have the lesser space harmonics, then higher efficiency, better power distribution, that means the reduced power per leg of the inverter, then improved fault tolerance capability, and this is the major salient feature of multi-phase machine, which is used for flywheel energy storage, because this requires a very high reliability system, and multi-phase machine offer this feature. So reduced rating of the switches because the phases are more, so the power per phase is less, so the rating of the power converter switches are low. Right? There is a possibility of torque enhancement by injecting low order harmonics in the control scheme. So major application areas for multi-phase machines are electric transportation system, like trains and, or the more electric aircrafts and electric vehicles, the ship propulsion. So in a dual three-phase induction machine, there are two three-phase winding sets, and these two winding sets, they are displaced by an angle 30 degree. So one three-phase machine is A, B, and C, and another three-phase machine is U, V, and W. So there are two sets of three-phase windings. They are displaced by 30 degree. The neutral can be isolated or the neutral can be combined together. So this is called asymmetrical three-phase machine, or asymmetrical, sorry, dual three-phase machine, or asymmetrical six-phase machine. This kind of machine is very much used in the literature whenever there is a application of six multi-phase machines. So each three-phase winding has three-phase machine has three-phase windings. They are symmetrically distributed by 120 degrees. Now, this is the mathematical model of the machine, the transformed model. There is a d-axis voltage, q-axis voltage. This is the stator voltages. Then these are the rotor voltages, and this is the x component of the stator voltage, y component of the stator voltage. These are the flux linkage equations, and this is the transformation equation for the stationary reference frame. And this is the decoupling transformation from alpha beta to the dq, the rotational reference frame, and the torque equation is given by this relation. So the machine phase currents, they are sensed and transformed into the rotating reference frame. This is the block diagram of the vector control scheme of flywheel energy storage system. And from the sensed currents, which is from the sensed current, the slip speed as well as the frequency are calculated according to the slip speed equations. The rotor flux angle is calculated from the sensed mechanical speed. With this vector control, the DQ component are used for modulating the active as well as reactive power flow. XY components are used for minimizing the losses. So the current components of rotating reference frames, IDS, IQS, IX, and IYS are compared to their reference values, and the errors are applied to the fuzzy logic controllers. The rules are given in this table. So the reference of the d-axis current, which is defined with respect to the rated magnetizing current and the rated flux. The fuzzy logic control observes the pattern of error signal and correspondingly update their output signal to match the reference value. The torque component is q-axis component, and the flux component is the d-axis component. So the q-axis reference current is generated according to the grid voltage, frequency, and power, and IQS is compared with the reference value of the q-axis is compared with the actual value, and the error is fed to the fuzzy logic controller. The fuzzy logic controller generates the reference DQ voltage, which are transformed into the original phase variable by using the inverse transformation of Park. Then the simulation case studies. These are the ratings of the machine which is used for the implementation of the vector control. Variation in the d-axis current, even though there is a huge variation in the q-axis. So that means these two are decoupled, and that indicates the true vector control is achieved. Employing a dual three-phase in this work reduces the power converter per leg rating as well, and it gives a very highly reliable system.